Hi, in this video I would like to talk about what I've been doing the past few months, what's the progress, maybe it's more progress on the MJ40 brute force development, rather progress on the actual pump, but we are getting somewhere and I will talk about it in this video. So firstly, about what's been happening since the last video which I made 3 months ago, about the first attempt to build a CFD. Maybe I didn't previously explain it properly, but what's the point of writing the CFD code? Well, the last year, 2025, I spent basically like most of the year when I tried to make progress on the MJ40 brute force, I spent it using experimental tests. First, I made tests on the pool. I made like 400 of them and optimized the pump that way. And then I tried, that didn't work properly as the results from the pool didn't properly translate into results on the lake. So then I went on the lake and I went there multiple times testing different iterations of the pump on the lake. But that also didn't bring any significant improvement over the MJ35. So I like now I'm thinking I need to change the approach, right? The obvious issue with lake testing is that I cannot make enough tests. Like if I drive to a lake, maybe I can test like tens of parts if I spend quite a long time there and if I have good conditions, if there is no wind, there is no waves and everything. But it's just not it's I'm not able to do enough of them, of those tests. I would need hundreds of tests in order to find something which is significantly better than the MJ35. And that is why what I'm trying now is to write a CFD code, which stands for Computational Fluid Dynamics, a code that will get the geometry of the pump and it will predict its efficiency by doing a fluid simulation. So what you maybe saw 3 months ago on YouTube was the first version of the CFD code which I'm working on. Here is a little recap of that. And if it is very unclear what you are looking at, then I suggest watching the old video where in the beginning I explained just a little bit about that. So here is what I did next. Thanks to writing that code, I had something in the computer which takes the geometry as the input from CAD. I have to model it myself, and then it predicts me how good the geometry will perform. But I needed to go one step further. I needed to automate the generation of the geometry because I still cannot really be sitting at the CAD and exporting 1000 of STL files and fixing the errors in them. So I went on and I used some math and surfaces to parameterize almost full geometry of the pump. The only part which I kept the same all the time was the exit nozzle, which, as it is quite organic, the shape would be difficult to parameterize. But all the other shapes, like the shape of the vanes and shape of both impeller blades, were parameterized using some parametric equations. This resulted in a parameter space of like tens of parameters, I don't know, maybe 30 of them. Here is an overview of that. And so what I did with that, I automated the whole process. I automated selecting the parameters so that the code thinks that they will work very nicely. Then it sends them to generate the geometry, and then it sends the geometry to run the fluid simulation, which outputs the efficiency and performance of that setup. This is then sent back as a feedback, and the selector selects another round of parameters. And this runs automatically. It takes many hours, and the fluid simulation runs on GPU, and it uses its full power. And it's basically it can heat your room up. And so I let it run for multiple days. And the result of that, or maybe first let's look at what the process of that was. Here I will be showing images of the last frame of the fluid simulation with the selected geometry. And see that the selector of the geometry is really quite stupid at first, and it picks many completely like nonsense options. But then I made it just a little bit smarter, so it started picking geometry that makes actual sense. So maybe you could notice that the most important change which the selection of the geometry ended up with was that the pump is now significantly longer than it was before. And so I took this as a result. This was the optimum that the simulation found. This doesn't mean that it is optimum in reality, and that's the problem basically. But yeah, I took the optimum from that, and I actually tested it. Here it is. This is the result of the optimization. It's assembled here, and as you can see, it is actually very long. But I thought, hey, let's give it a try anyway. So I gave it a try. Yeah, but unfortunately, this still doesn't work. This is the performance of that is quite underwhelming. It's very poor. The main problem is that the simulation to predict accurately, I need to predict accurately two things. The first one is the flow rate, and that is running already quite okay. This the flow rate seems to be like it matches the experiments which I did before, like within a few percent of error. So that sounds good. But the other thing which I need to predict in order to calculate the efficiency is the torque requirement by the motor. And from the first version of the CFD code, the torque is very off, like it's two times off or so. So I still tried to use that, but it is not accurate enough. So because the torque is off, then the efficiency is off too, and the optimum which is found by this code just doesn't match the optimum which would exist in reality. Yeah, so the question is like what to do better, how to change the simulation to make to give better results. But the first thing I had to do was to switch the programming language because I was writing it in Python, and despite using like GPU accelerated libraries, I couldn't make go it fast enough. So then what I spent a lot of time doing was rewriting this all, and I am still working on it. I rewrote it into C++, and also it still runs on GPU, but it is now like 15 times faster. And it also allows higher resolution, which means if you imagine the fluid simulation as if you had as if you are watching a film and it has so low resolution, you cannot see the faces properly, right? And if you increase the resolution, you can see everything better. And it's the same with the fluid simulation. Now the new version allows up to like 10 times more resolution, like 100 million of pixels, about that. So that's like the first thing I had to do. And there is the other thing, which is boundary condition on walls, which is not like I won't go into detail about that, also because I don't properly understand it yet, and I need to focus on it more. So I might be rewriting the boundary conditions for walls, making more progress on it. But anyway, I took the new code. This is the newest version I have, and I don't have a version which can simulate the pump yet because there is the rotating impeller which has to be programmed like using some new features. But I already have a version that can simulate the intake. So that is what I will show you now. I will show you three different versions of the intake, and the first simulation I will show you is the MJ35 intake. There is just a little bit of simplification. There is no intake grate, like there are no bars which would prevent debris from going in there because the resolution is still not high enough to capture details about that. And also there is no drive shaft, and there is also obviously there is not the rest of the pump, but the flow in the intake should be somehow captured by this anyway. So as you can see, according to the simulation, there is a lot of separation on the roof happening in the intake which has no loading rate. And there is also separation uh, once it reaches the end of the bottom ramp, there is separation too. For example, I didn't focus on that at all when trying to optimize the intake. And according to the simulation, the efficiency of this MJ35 intake without the loader is about 40%. So then I went on and I added the loading rate. And the reality is that the loading rate should add efficiency, or at least it should like somehow change the resulting behavior of the pump, because in reality it improves the top speed by about 5 kilometers per hour, which has been measured multiple times by multiple people on different boats. So the loading rate helps in reality, and now here is what it does in the simulation. So in the simulation, as you can see, even with the loading rate, there is still separation of flow happening on the roof of the intake, and there is also new region of separation just behind the loading rate, which just by looking at it, it makes sense, and I actually thought this would be happening. But what the simulation gives, what it says about this is only 30% efficient. So the simulation is telling me, hey, the loading rate should make things worse, but in reality this is not true. So this is like immediate discrepancy I can see there. So something is still wrong, but it is also a question whether the improvement in top speed in reality when using the loading rate, whether it comes from increasing efficiency of the intake or changing the angles of the flow which approach the impellers, because you can have the two intakes, they will have the same efficiency, but one of them will be sending the flow into the impeller at a different angle, and that will change efficiency of the impeller, and so that it is not necessarily caused by the by improving efficiency of the intake, but it can be just angles of the flow, right? What you can see, there is separation happening. Like it is almost certain that it is happening in quite a big extent. So I went on, and I also had this in mind when designing the MJ40 Bruteforce intake. So then I tried to simulate one of the MJ40 Bruteforce intake versions. There are multiple of them, but this is one of them. And as you can see, this is looking a little bit better, and also the simulation is reporting that this is 50% efficient. But it seems like it should be made even longer, the intake, but that's also like I cannot extend it forever, because the boat has to like it has to look somehow, and there is not infinite amount of space behind the boat. Like, well, there is, I just don't want to extend the intake forever, right? There should be a different way how to bend the flow upwards without extending it so much. And also I cannot extend it too much in front, because there must be the electric motor somewhere. But maybe there is a different way to add a loader which will fix all of this, like a different kind of loader or multiple loading grades. I don't know. And this is basically where I am now. I want to continue working on the simulation to first make it more accurate. Maybe I will have to do it anyway to run benchmark tests which have known analytical solution, to compare it to something reliable, and to see if the simulation is doing something meaningful. And then I want to find a good intake. And maybe what I will do is that once I find a good intake, I will take the outlet of the intake, what it calculates, and then I will use it as an inlet for a new simulation where I will simulate the pump, and I will once again try to do a parametric optimization. Yeah. So that's the plans for future. And as you can see, like this is not a short process. This just takes time. I still want to try to get the pump ready till this summer season. So wish me luck. I wish you luck too if you are building a boat. And for now, that's all from me. Thanks for your attention, if I still have it, and have a nice day. Goodbye.